Okay, so I guess we can start. Hello, everyone. My name is Yossi Aitijin. I manage the UCX team at NVIDIA and co-maintainer of UCX project. So in this session, I'd like to bring up our actually long-time discussion. We have it every session. It's a very interesting and challenging topic, how to improve our GPU support. Especially how to make sure that our out-of-box performance without any special setting is good enough for all use cases that we have. And fortunately, we have many of those. So reminding where do we have GPUs in this in our protocol software stack. So on the UCP, the top layer, we handle things like GPU memory detection. We make use of the memory type cache, and we adjust some thresholds to disable shortcuts, essentially disable short messages whenever we think that there is a possibility to have GPU memory with this context. In addition, recently added APIs to pass memory type as a hint. We have memory type endpoint, which is a collection of local endpoints, which are used only to transfer data between different memory types, mostly from a host to GPU or vice versa, and it's instantiated for every memory type. We actually support GPU memory in most of our communication APIs, which are tag matching, active messages, stream, and the Rdma and atomics with protocols v2. We have a rendezvous protocol, which is a pretty complex scheme today. It has a different logic scattered in multiple places to select optimal lanes, to handle a rendezvous fragment spool, and select zero copy rendezvous versus pipeline protocols. On the UCS side, we have a topology detection. It caches all system devices and able to give some approximation of bandwidth and latency between different devices. We have the data structure that is the actual memory type cache, and the whole definition of the memory types. On the UCM, yeah. So on the UCM, we have memory hooks to handle allocate and release calls for CUDA memory. And this way we can populate a memory type cache and have a fast detection of memory type without actually going for the driver or for the memory domain to query from the system. On the transport layer, we have a common API for a GPU transport that is implemented by ROCm and CUDA. The basic operations include put and get operations, both short and z-copy variants to support copying between memory types. And the API that we extended and added in this year, that is a query memory attributes. Today, it provides support to detect the actual allocation size of GPU memory. For example, if you're sending just a small piece of GPU buffer, we're able to detect that it's a part of a larger chunk and to pin all of that, mostly because the cost of pinning a large region once is much smaller than pinning it multiple times in chunks. Well, we don't actually need to bring pages from disk or something like that. They're already there. And for Rdma transports, we have some code that detects a GPU direct support. It queries a presence of driver-specific files like NVPRMM, and we actually plan to get rid of it to some extent once we move to Dma Buff. So to put all of it together, what we did recently in last year, so we continued the implementation of protocols v2, implemented the pipeline protocols, Rdma and atomic APIs with GPU memory, plus support for that in UCX perf test, and of course running everything in CI. We improved the topology detection. It's now based on more accurate walk of CSFS and checking if we have a switch device, or we go to the root complex, which means a slower bandwidth, or we go to the cross CPU interconnect, which means even slower bandwidth. And we're probably going to extend it even more in the future. The CUDA driver hooks are now based on binary parser, so it can support static link. The memory tape cache is now global, so some transports could select, for example, in CUDA, we select the stream based on memory type. So different types of transports could use the different streams. They would not block each other. We can auto-register the whole allocation, which means that since now we have the memory query API, we have option according to some thresholds to register the whole CUDA buffer, which improve specific cases. For example, UCC collectives that use a GPU memory. In addition, we select CUDA IPC based on NVLink topology. In some cases, we would like to disable it or some operations of it. If NVLink is not available, then we actually go for PCI Express. And we started the implementation of a device memory pipeline, which means that rendezvous fragments would be on the device. And the piece that was done so far is to have a rendezvous fragment pool per device that is created on demand in the UCP layer. Coming next in 2022, we plan to add more logic and hopefully complete the device memory pipeline for CUDA IPC. And we want to add an intranode two-stage pipeline which means that instead of copying memory across host twice, we can copy it only once. We want to add the Dma Buff Support actually in 1.14 release. And we want to spend some time, actually probably a lot of time, on tuning out-of-box performance of Proto V2. Since most of the building blocks are there, but the performance is still not same or better for all cases, and that's why it's not a default today. Specifically, things like eager rendezvous threshold or select pipelines versus GPU direct. Also, we plan to improve our multi-context support, namely that users would not have to set context before doing some UCX communications calls if they're allocating memory from different contexts. And hopefully UCX would be able to query the memory, identify the relevant context, and use it automatically. So now going over the features that we have in more detail. Actually, it's kind of like to make it an open discussion. And since we do not have everything figured out already, so we'd be happy if people would chime in and add more comments as we go along. So the use case for that is for device memory pipeline. There are three main use cases. So processes on the same node exchanging CUDA managed memory. CUDA managed cannot be used with CUDA IPC. So we have to copy it to some other buffer and then exchange it by CUDA IPC. Today we're using host buffer, but it's not efficient because it has to go for PCI Express. But actually we could copy it from GPU to another memory in the GPU and then transfer it over NVLink. So in addition, if we have processes on different nodes that exchange CUDA memory over RDMA, GPU direct is fast, but we cannot register the user buffer because it's too expensive. For example, we use some buffers only once, so we wouldn't like to register a buffer that is used only once. We'd like to do some kind of copy, or because the bar is small, for example, T4 devices, so we can't actually register the whole GPU memory. We have to use some kind of bounce buffers. So today, applications that suffer from these issues have their own bounce buffers on GPU, for example, in Rapid Spark, and eventually would like to provide a better solution for applications. So they could do just send and receive directly without adding their own bounds buffers. So the approach we took is that in UCP layer, the rendezvous fragment pool is for every system device, and we initialize it on demand to not initialize pools that we're not going to use. And the protocol should select the device memory according to user buffer locality. So we go and query the system device of the user buffer and select it accordingly. So the problem here is that the receiver needs to select a rendezvous fragment that is NVLink reachable from the sender, or a host fragment if it's not reachable. And that's a challenge. We actually discussed it quite a lot internally with Akshay and the vendor, but could not find a good solution for it yet. The problem is that the receiver doesn't know in advance if the send buffer is going to be reachable or not for NVLink. So it has to select, if it selects a GPU buffer and it won't be reachable from the sender, then we cannot actually do the rendezvous protocol. But if it selects a host buffer and it is reachable, then we're missing out on the opportunity to use NVLink here. So we thought about sending maybe more information in the rendezvous header, maybe send information about the bounds buffer, so the receiver could have more information and select the right thing. And another direction is to have a multi-stage rendezvous protocol, where we first, where if the sender, after getting a reply from the receiver, detects that it's not reachable, would maybe send additional message and try again with bounds buffer data. So Akshay, did I get it right? Or do you have any comments about that?
No, that captures the problem.
Okay.
Can you catch the failure, Yossi, in fallback? Essentially catch the failure in cache for this buffer, what you learn.
So you mean a combination of multi-stage rendezvous, but with addition of some kind of remote cache about what is reachable or not?
Yeah, because on virtual address, you eventually can like recycle our cache to learn.
That's actually not bad. You mean remote cache, right?
Yeah. Like either way, it's like, depends where your problem. You can solve it either way, but if it's receiver, yes. You can try, like essentially best effort fail, cache what you learn. And next time you retry already with the right.
That's actually good, I think. What do you think, Akshay?
Do we send information about the bounds buffer details today at all as part of the control?
Well, no, but maybe we can do it as we do today. And if we get RTR and we see that, I mean, the RTR would be the details of the bounds buffer of the receiver. And then if the sender would see that the receiver bounds buffer is not reachable by NVLink, it would send something like a second RTS, but not with new tag or something like that, but with request ID.
So Yossi, so what you mean there is like the RTR would include both the actual receive buffer and also the details of the potential bounds buffers that could be multiple locations. Is that right?
Actually, I think the remote cache has to be on the receiver. Now that we're thinking about it, because the receiver is the one that is going to decide which buffer type, which memory type to use. So if the receiver would receive a second rendezvous control RTS message, which means the sender has failed, maybe the receiver can cache some relation between the virtual address of the sender and the actual bounds buffer type that was successful for that receiver. I mean, for the memory type for which the receiver eventually got the rendezvous acknowledgement instead of some kind of retry message. And worst case, we can always do the retry and then optimize with a cache.
That sounds good. I guess we'll have to work through the steps, but on paper that sounds good.
Okay.
And you see, another idea is it optimal to have a endpoint to endpoint eager RDMA kind of setup, pre-setup, and with limited buffers, and use the IPC events to just issue all of the memory copies, but the dependency is created with the events.
I don't think I understand the.
Do you remember in MXM we used to have a eager RDMA?
Yeah, where you do RDMA instead of falling on receive queue.
Yes. So is it? I mean, in the RTS, can we grab one slot of buffers and share it and just continue with copies, and then?
Oh, you mean instead of sending a control message?
Yeah.
But this means that it has to be reachable for IPC.
Yeah, I mean, we need to have this maybe in the first transfer or beginning. I mean, we need to, for that specific GPU, we need to check the connectivity and set up that.
But in order to write, we need to do CUDA mem copy, right?
Yeah.
But so I think isn't CUDA copy more expensive than doing some kind of shared memory host-based control message?
So we are writing, we are writing into sender side, we are writing into CUDA memory.
Yeah.
And then let's say we have only 2 buffers for that specific target. We can issue all the mem copies in pipe, with the, dependency. Then we will send that in RTS, which probably we will give the information of which slots are using for this transfer, and the receiver will map the IPC, and then in future, if we are getting the same slot, then we can just do the copy out from that sender copied in message.
Do you mean that it would improve the data transfer itself or the control messages?
I don't think the control message data transfer will improve, but probably if very, very large messages, we might work with a limited set of.
So there are the optimization that's an add-on, which is beyond the scope of this challenge, is that you would want to use IPC events, and the IPC events would serve the same purpose as exchanging control messages, because you're recording events and having the remote side get notified of completion of mem copies through these events. And it would bring in both overlap improvements, and it would potentially improve control message handling. Is that right? It won't improve the bandwidth of the individual operations because they're ultimately the same.
Sounds like put with signal abstraction or something like that.
Yep, it's very similar to that.
So if we added something like put with signal to UCT and implemented it with events for the CUDA transport case, and then the rendezvous pipeline protocol would use a put with signal abstraction instead of put plus ATP.
So the signal is small message shared memory flag?
Today, yeah, ATP is in a regular shared memory.
And signal?
So
signal, I thought of the signal would be the abstraction for event, because we can't use CUDA event directly from UCP.
Yeah, and in the case of put with signal for the CUDA IPC case that we're discussing, the signaling would be implicit in the fact that the put itself, which involves issuing a mem copy followed by recording an event, an IPC event, that itself serves as the signaling. It doesn't have to be the case that the signaling needs to be instigated by UCP by issuing an SM write, for instance.
But receiver has to know if the signal is if the record is issued. Otherwise, it became a no op right at the receiver. Still, we need a
and that is by waiting on events. I mean, and that's essentially how it would work. Either wait or querying Ipc events.
Then how do you
Does that
share
make
that
sense?
Ipc event to the remote side?
That needs to be handled as part of the exchange, like the initial exchange.
Maybe even for EP creation.
As soon as you're able to detect GPU context and you're able to allocate GPU resources, just like how we do with streams today, alongside you would allocate Ipc events as well. We don't allocate Ipc events today. We allocate only local events to query the status of outstanding CUDA and copy operations, but you would also allocate Ipc events. And potentially you'd have to exchange some details of each of the events on the remote side, because that's how you would know which event to wait on.
Basically, we need an event per slot per segment, right? We cannot.
Maybe we can count. Is there some kind of counter event?
I don't think there's a counter abstraction today. The only mechanism that I know of is where you actually create Ipc events and you exchange them through some outer band mechanism. And later, the remote side, which is waiting for completion of memory operations, would essentially query these Ipc events and these opaque handles, and then upon completion, it would know that the remote side mem copy operations are complete.
So, but is it really going to be better than sending control message for host memory?
So basically, you can avoid step-by-step interaction that happens between send and receive today. In the sense that today in a pipeline, we issue a copy, and then we notify to the remote side, hey, I've completed this copy. And then the remote side then goes on to issue a local copy from staging buffer or so on. This constant step-by-step interaction can be stopped. And instead, you dictate upfront that I'll use all these Ipc events to begin with for this transaction. And all you need to know is look for these events to complete locally. So you can essentially eliminate all the sender and receive control message exchanges. Although I don't know.
So you mean the control, actually, the progress would happen on the GPU stream?
Right.
Okay. So the main benefit here is that it would make progress regardless if application is calling UCP worker progress.
Yes, that's an added bonus. Yep. If the sender enqueues all copy operations and records all events, then receiver doesn't have to call progress at any point. These are happening. And because the receiver has also enqueued everything onto streams, like waiting for events and issuing subsequent copies, it can essentially enqueue all the copy operations.
Basically, one advantage is we can work with a very limited set of fragments. So let's assume we need to send 8 fragments and we have only 2 of them. Then the sender puts the first one and records it, and second one and records it, and waits for the first one to re-record. I mean, the receiver is waiting for first one to trigger. Then that will issue out, and then again records an event. So then the first one, sender will basically wait for receiver to trigger the receive complete. Then he can, he can just, without extra control, with those 4 fragments, you can issue basically any number of sends.
Right.
Oh, that sounds very, very nice. I think, but we're missing quite a few abstractions on the UCT layer, like triggered operations or doing things after you receive the signal in order to really connect everything here.
Maybe in the first stage, we can just go without events, and then an optimization later we can.
How would you do it without events?
Without events, basically for every fragment, we grab an issue and then once poll it, once complete it in send it. I mean,
You mean
it's as it is now, right?
yeah, but we are, I mean, the receiver is going to map the sender fragment, right? In that case, and then, or it can find it in the cache, then copy out.
You mean useless fragments?
No, use either it's up to, yeah, useless fragments or infinite fragments, but every fragment will have a control message.
So we can unite the control message that we're passing now on host memory and poll on it essentially on the CUDA transports.
Yeah.
And in order to poll, we have to do CUDA mem copy, for example, from GPU to host and check its value or something like that.
So I mean,
I don't think that's. I think that there were, if I understand right, you meant that as part of the control message, you send the event itself, right? The case that you pass something through.
Basically, maybe in the initial control message, we need to say how many slots and its corresponding events to the remote side.
Right. So you see, to summarize, it's not the case that you signal by writing a flag on GPU memory and then copying that and seeing what the value is to see if the copy is completed. But instead, it's issuing the data payload as it is, but also sending the event associated with it and polling it on the receive side to see if the copy completes.
So polling on CUDA. Yeah.
In the control message, we have to wait for sender to complete that copy. Then only we can send the, control message to receiver to copy out, right? But with event, as soon as you issue the copy, you record it and give it to the receiver.
So I mean, we can avoid the round trip of the sender.
Yeah, control.
Because in CUDA Ipc, we first wait for CUDA Ipc to complete, and then the sender has to send another message, and the receiver waits for it. But in your suggestion, the receiver could receive the control along with the data and avoid waiting for the sender again.
Yes. Yeah.
Okay. Yeah, so we have quite a few ideas here. So yeah, regarding the last one, I think we can start thinking about some kind of extended rendezvous header for the retry. I mean, it would work. Maybe it would be a extra control message, but we can always optimize it away with some kind of cache. Yeah, okay. Any more things before we move to the next thing? Okay, so intranode two-stage pipeline. It means that when we have two processes on the same machine that need to exchange CUDA memory, and we do not have an NVLink available, today what we do is that we CUDA copy from send buffer to host a rendezvous fragment. Then we use some kind of kernel assisted copy mechanism like KNM CMA or XVMM to copy from the sender host fragment to the receiver host fragment. And then the receiver also has to CUDA mem copy to the receive buffer. But a better protocol that is actually used by OpenMPI SM-CUDA would be to use only one host base fragment and share it between the sender and the receiver. So the sender could copy to that memory and the receiver copy out of it. but obviously we have a few issues with that. So we need to somehow manage and reuse the shared rendezvous fragments, because the actual cost of mapping some shared fragment that you get from the sender is not very small. You need to mmap or do SHM attach or something of that sort in order to use that fragment. That's why we need some kind of cache of remote map fragments, and it's going to be per endpoint because it's per specific destination. And we actually have a similar cache in XPMM on the XPMM transport layer. On the XPMM transport layer, we use it to make the UCP ARCI unpack faster. And what we could do here is, first of all, make the same cache in UCP. And second, we can try to eliminate the cache on XPMM, which means that the UCP-based cache will also cache remote keys and reuse them across multiple rendezvous transactions. And on a more general note, it looks like in coming year, we'll need to do some few changes that move logic from UCT to UCP, because things that solve problems on specific transports now have to be generalized, and we can't keep them in UCT anymore. So this remote cache is one example. And we'll also, on the next slide, we'll talk about moving the registration cache itself to UCP. And by the way, when we use this shared fragment pool, we don't actually need a KNM or CMA or XPMM. It would be enough to use one of the basic memory mapper transports, like POSIX or System 5, which are capable of allocating shareable fragments. And also, there's a small trick if we want to avoid the increasing UCP endpoint size. We can just add a new hash table where the key is a combination of endpoint and the remote virtual address, and the value is the cache entry.
You see, what do you mean by endpoint size there? Like when you said increasing endpoint size?
Yeah, so one of the things that we need to keep in terms of optimization and scalability is to make sure that the UCP endpoint memory footprint does not increase as we add new features, because it's a structure that is allocated for every connection. Actually, this is the same case with UCP ARCI. So we do not want to add something which depends on the number of endpoints, only maybe on the number of usages. And I mean, we probably don't need any cache entries for internode endpoints.
I had another question for this. Why do we not already have something like this for host-to-host transfers? Is it because there's already CMA, KNM, and XPMM that we never decided to have shared staging buffers?
Well, for hosts, we don't really need staging. So we want to copy directly from one host to another. I guess we can think of case for CMA, KNM, or XPMM are not available, but actually on all modern kernels, we have a CMA. So it's not really a problem. Okay. So the next thing is that the Dma Buff Support, which we actually started to discuss on one of the UCX meetings, the bi-weekly meetings. And just to revise on our design decisions, is that the GPU transport is going to expose querying a memory region file descriptor, and the Rdma Transport is going to support registering Dma Buff memory with a file descriptor. So probably not probably, but actually what we decided is that to extend the UCP mem query function, to add an optional file descriptor as an output field. And we're also going to extend a UCT memreg function to pass optional input file descriptor. And if it's specified, it would mean that it's a Dma Buff registration that should be done by calling IBV reg Dma Buff MR API in Rdma core. And the UCP layer is responsible of getting the file descriptor from GPU transport and pass it to RDMA. And we want to close it as soon as possible to avoid exhausting file descriptor space, which is quite limited. So as part of this task, it seems like we need to move the registration cache to UCP. Obviously, there are pro and cons for that kind of change. So besides the amount of work and changes required to do that, it means that the UCT layer would not be as performant as UCP. It means that if some UCT users want zero copy and a good level of performance, they would need to create their own and maintain their own registration cache. But we do have the facilities in UCS to do that. For the time being, we probably can keep both registration caches, and we first search in UCP, and only if it's missed, we also search in UCT. It would add the overhead of additional data structure, but probably would not hurt the actual performance. But if we do make this change, it would be more friendly to Dma Buff, because we would not need to get a file descriptor if the cache is hit. So the vendor also proposed intermediate step that we can query the UCT layer twice, and only if it fails to register without FD, it means that it's a cache miss, and we need to pass FD again, and this time actually get the file descriptor from GPU. But it still means extra overhead, and there are additional benefits to moving the registration cache. So we can reduce some of the software overheads for zero copy path, and reduce some of the data structures and loops and ifs that we have today for zero copy. Because in many applications, especially non-MPI, things like block storage or other data-driven applications, the zero copy path is very important, and we need to reduce the software overheads of it. In addition, it allows potential optimizations and ending logic in UCP, things like tracking user buffer ID. We cannot really do it today because the entity in UCT that keeps the registration cache, which is IB, is not the same entity that allocates the memory, which can be CUDA, for example. So it has to be some common place. Also, it would allow future optimizations that select protocols depending on the outcome from the registration cache. For example, if a registration cache has a miss, we don't have to register memory immediately. We can count usages on a buffer and register only after a while, or maybe even start asynchronous registration, and in the meantime do bcopy protocol. And maybe we can also look at the registration cache size and how many memories spinned, and according to that choose whether we want to register more. Because in UCP layer we can take into account the actual registration cost that is going to happen depending on the hit or miss, and not the amortized cost that we expose from a UCT layer today. Any comments about this so far?
So this comment that we have to keep our cache in UCT, at least for a while, means that we'll keep it until all the mentioned optimizations are done to amortize the cost.
So I guess we'll have to, yeah.
I just didn't get I mean, this at least for a while. What would be the trigger to remove it then eventually?
So maybe we want to give some grace period to UCT users to add their registration caches into their codes.
So now I get it. You mean UCT users, customers, not UCP, which are using UCT
Yes.
directly.
Yeah, like BTL UCT, for example.
Oh, Huawei probably. I see. Thank you.
So continue with the protocols. So as a reminder, the main idea in protocols v2 is that instead of some rigid thresholds or many branches and checks, we can calculate the estimated performance of all protocols and do some kind of mathematical intersection and find the best for every protocol for every message range. And the main idea is demonstrated in this drawing. However, it turns out that the actual implementation is not so easy. I mean, it's not very hard to do the intersection and do the protocols, but the challenging part is get all the performance models right. And we really have to get them right, and they have to be pretty accurate. Otherwise, the thresholds will not be correct. And in some cases, if we change the protocols performance estimation just a little bit, it has a big effect on the threshold. But the advantage here is that we can and actually supposed to tune every protocol performance model independently and not necessarily worry about the thresholds. However, it turns out that as we complicate the performance model and we have especially rendezvous protocols that are a combination of performances of multiple protocols, we need to add more debugging infrastructure into that. Today, we have just a lot of traces and messages and protocols splitting their own performance estimations. And it's quite hard to keep track of how everything is being put together and why is the current threshold being selected and why, for example, the eager to rendezvous threshold is 16 kilobytes and not something else. So we have some preliminary thoughts of somehow representing all the protocol decision in some data structure and allowing users to maybe by environment variables to ask UCX to output the justification or the reason to selecting some specific thresholds. So if we look at the overall plan, we have already the infrastructure, but we currently continue to work on fine-tuning the performance estimation. For example, these days Rdma improved the pipeline performance estimation, which is how we estimate the performance of a protocol that consists of two parts that run in parallel. We have all the tag matching and the RMA and atomic protocols in place, including a rendezvous pipeline, both get and put. And we're currently quite happy with the topology awareness code. It gives quite good estimations on a few choice platforms like DGX, Intel, and AMD without NVLink. Active message are currently work in progress. We already merged the short and big copy part and plan to merge the rest for the next release. Stream is not started yet and it's currently not a very high priority. The client server connection is also work in progress. But we do have the advantage here is that we can select the protocols as the connection is being established. So some users complained that when we start the communications, we always start from bcopy message, even though rendezvous is actually possible. And this happens today because before we actually establish the connection, we can't know for sure that it's going to support rendezvous. So we kind of fall back to the minimal support, which is bcopy. But with Proto v2, we can defer or re-evaluate the protocol selection when the connection is actually established. So we can start with rendezvous or whatever is best right away on the first message. In addition, we want to do the error flows for the new protocols. The plan is that every protocol definition would have some kind of abort function or cancel function. So instead of having a big if like we have today, how to clean or purge information and request for every kind of protocol, we can define it in a localized way, and it would be much more extensible and structured. And the most probably time-consuming and important part is to tune out-of-box performance and make sure that our performance estimations are actually matching the actual performance. So the next step that we plan to do in the coming year for the next 3 releases are finish implementing all APIs. If we can reach a good level of performance, we can remove existing protocols and much of the current AP configuration code. Plan to add the rendezvous protocol with IOV list. So since this is something new, and it could be quite complicated, we do not plan to add it for the V1 protocols. Now that we add the WAR compatibility, we can use an interesting scheme to select protocols. So we can say that one of the criteria to select a protocol is the maximal supported version of the remote side. For example, we can say that every side supports up to version X. And if we have some newer worker in the communication, it would know that it cannot communicate with the older version with any kind of protocol which is larger than version X. So this way, if we plan to change wire protocols of some of the data path communications, we should never change existing protocols. We just add new protocols, but they would have a higher priority or better performance estimation in that case. And we fall back to old only if no other choice. And the protocol version is exchanged as part of the UCP worker address. And as we mentioned before, we need some kind of more detailed trace and debug of why something was selected. It's a question that user ask us and the people running applications ask us, and it's never easy. It's not easy today to give a good answer to that. And we're also looking into a topology injection, something which is possible today with Nickel, to provide some external file like XML on systems where CSFS does not have meaningful information, like virtual machine systems. Okay. So actually, yeah, I think I'm also finished quite early. Any questions or more topics to discuss with regards to GPU?
Yes, back in the days we discussed about providing a way to pass stream GPU stream information through the interface. So I'm curious where this stands. If they're still interested in something like this.
So we had some discussions about that. Turns out it's not such an easy problem to solve. We need to eventually. It turns out that we'll have to provide streams per operation basis. It's not something that we can provide to worker or endpoint, and we need to make sure that all the layers actually use that stream for communication. And so for now, it's not a priority or in the definitive plans for this year.